Hello class, Dr. Banks here. So let's continue our discussions on the properties of Laplace transform. So properties of Laplace transforms. So this is the part 2 of this particular properties. Okay, so the part 2, let's start with property number 5, okay, which is called time integration property. Okay, this is called a time integration property. So we're going to prove this particular property. So now here, if x of t gives what? If x of t gives x of what? S. Okay, here Laplace what? Transform. Okay, then we're going to have here, sorry please, before I write it then, okay, let me write my ROC. My ROC here is what? R. Okay, R. Okay, then I'm going to have this particular condition, that time integration property. Okay, so with time integration property, then I'm going to have here, if I should integrate from minus infinity to what? To the current time, which is t. Okay, here x of what? Tau, the tau. Okay, the tau will have a Laplace transform. A Laplace transform of what? X of what? S. X of s over what? S. Okay, and the ROC here is going to be what? R intersection our current one. Okay, RE of what? S. Okay, RE of S, which is basically greater than 0. Okay, so basically let's see how we can actually prove it. Okay, so here we use the inverse Laplace. Okay, we use the inverse Laplace transform. Okay, we use the inverse Laplace transform. Okay. So to use the inverse Laplace transform, we know that x of what? T is equals to 1 over what? 2 pi j into what? Sigma minus what? J infinity, sigma plus what? J infinity. Okay, into x of what? S into what? S what? T d what? ds. Okay, ds. Okay, so now here what we do is that integrate. Okay, integrate both sides. Integrate both sides. Okay, integrate both sides. So if I integrate both sides, then what I'm going to actually have is that I'm going to integrate this particular part. Okay, I'm going to integrate here. All right, and then also I'll integrate this part. Okay, so here integrating both sides, I'm going to have here, but even if I'm integrating here, I'll replace this t with tau. Okay, so minus infinity to what? T. Minus infinity to t. X of what? Tau the what? The tau. X of tau the tau. Then here I'm going to actually have is equals to 1 over what? 2 pi j. Okay, here. Okay, into what? Okay, like this. Okay, so here I'm going to have x of what? S. Okay, x of s into what? Integral of what? Here minus what? Infinity to what? To t. Minus infinity to t into e of what? S what? S tau. Okay, S tau the what? The tau. Okay, so here it's like this, and the whole of this is what? ds. Okay, so this is what I'm going to actually have. Okay, so now if I have this one, so here I'm going to have t. Okay, integral. Okay, like this. Okay, x of what? Tau the what? The tau, which is equals to 1 over what? 2 pi what? J. If I integrate here with respect to the tau, I'm going to have what? S. Okay, and s is going to what? Divide. So I'm going to have integral here, sigma plus j infinity. Okay, sigma minus j what infinity. I'm going to have x of what? S over what? S. I'm going to have this one. Okay, and then I'm going to have this one. Okay, e s what? Tau. Okay, e s tau. Okay, and then I'm going to have what? ds. Okay, so if I integrate, this is what I'm going to have. Okay, so if I have this one, then my proving is complete. I'm done with the proving. Okay, because I set out to achieve this. Okay, and you can see that I actually have this one within my equation, so it's achieved. So now what is going to happen is that if I take away this s, every other thing here, okay, every other thing here is the same thing as I have here. So if I take away this particular what s, then everything I have here is what? X of t, because this one is what? Inverse Fourier transform, and inverse Fourier transforms gives me what? X of t, and I know that x of t is the what? X of t is the what? It has a Fourier transform of what? X of s. So I can write what? X of what? S, and then I can bring my s, and then here I can have what I have here as what? T minus what? Infinity x of what? Tau d what? The tau. Okay, x of tau the tau. Being the Fourier what? Transform. Being the Fourier, being the Laplace what? Transform of this one. Okay, and then my ROC is going to be R intersection what? RE into what? S greater than what? 0. Okay, so basically it is achieved. Okay, it is achieved. Okay, if this one was to be, if what I have done here were to be Fourier transform, then you can refer to our properties of Fourier transforms. Then I was going to get what? Minus infinity to what? To t, x of what? Tau d what? The tau, being what? The Fourier transform of what? X of what? Omega. Okay, into what? J omega. Okay, all right. So, and then this is how I was going to what? Have it. Okay, and then it occurs at what? X of what? 0 being equals to what? 0. Okay, so let's go to the next property. So let's do property number 6. So property number 6 is called what? Differentiation. In differentiation in what? S domain. Differentiation in S domain. Okay, differentiation in S domain. So here we have if x of what? T, okay, has a Laplace transform. Okay, a Laplace transform of x of what? S. Okay, and it has an ROC of what? R. An ROC of R. And then we have this one. Okay, we have another Fourier transform. Okay, let's say x of what? T, having a Fourier transform of minus d on what? ds. Okay, so differentiation in S domain. So S domain, so x of what? S. Okay, and here it will have an ROC. Okay, which is also what? ROC, an ROC which is also what? R. Okay, all right. So here, basically, here is what? Minus. Okay, so now let's see how we can prove this particular, prove this one. Okay, so now we know that the Laplace transform of x of t is, okay, x of t equals here, okay, so x of what? The Laplace transform of, sorry, we cannot have the Laplace transform of x of t, okay, is x of what? S, sorry, x of s. So that here becomes x of what? T. E minus what? St d what? dt. Okay, so this is what we have. So now differentiation in what? Time domain. So I'll differentiate, let's say, differentiate both sides. Differentiate both sides. Okay, because it's differentiation in what? Time domain. So I will differentiate this side. D of what? X. Okay, I'm sure we are already very familiar with this particular equation, that Laplace transform of x of t is x of s is equals to this. Okay, we are very familiar with this equation. Okay, and then so here differentiating both sides. Okay, in time what? In s domain. S domain means that it's not time domain, so I cannot write here the t. S domain means that what? The s. Okay, so it's equals to here. Okay, minus what? Infinity. Here is what? Infinity. X of what? T. Then I'll differentiate this part. D of what? ds into what? E minus what? st. Okay, into what? Into the t. Okay, so I can have this one. So now if I have this one, then what I can do is that I can, if I differentiate here, I'll get what? Minus what? T. I'll get minus t. Okay, so I can have d on what? ds into x of what? S is equals to here infinity minus infinity. Okay, I can have minus what? T into x of what? T into e minus what? st. Okay, d what? dt. This is what I can have. Okay, this is actually what I can have if I should do this what? This differentiation. Okay, now this minus here is a constant. I can take it what? To be here. If I take it here, then I'm going to have minus d on what? ds. Okay, into x of what? X of s is equals to what? Here infinity minus what? Infinity. So I have t into what? X of what? T into e minus what? st d what? dt. This is what I have. Okay, so now you see that everything here is what? Everything here denotes, if I take away this t, everything here is what? X of s. X of s. Okay, and I know that x of s is actually the Fourier transform for what? X of t. So instead of x of s, I can write what? X of t, so that I can have minus d on what? ds into x into what? Into x of what? Of s. Okay, which is equals to t into what? X of what? Of t. So sorry, I am sorry. At the beginning, sorry, this place is positive. It's not negative. Okay, it's positive. It's not negative. It's supposed to be. It's supposed to be t. Okay, it's supposed to be like this. T into what? X of t, which gives a Fourier transform of what? Negative d on what? ds x of what? S. Okay, so please, it's like this. Okay, so you can see that that's the same thing I have gotten here, and the ROC doesn't change. The ROC is R. Okay, it's R. It doesn't change. Okay, so basically that's how you can do this particular proving. Okay, so now I think we can go to the next one and then do that one also. Okay, we can go to the next one and do that one also. So we can just do, okay, so we can do integration in time domain. Okay, so what we just did was property number 6. Okay, this will be property number 7. Okay, so this is what? Integration in time domain. Integration in time domain. Sorry, not in time domain. Yeah, why should I make this mistake? It's we did differentiation in S domain. Okay, this is integration in S domain. Sorry, integration in S domain. Okay, so let's see the integration in what? S domain. Okay, in S domain. So now integration in X domain. If x of what? T gives a Laplace transform of x of what? S, then x of what? T over what? T. Okay, will be equals to we'll have a Laplace what? Transform of here in S domain. So S to what? Infinity. S to infinity. X of what? S, okay, into what? ds. Okay, here our ROC remains what? Our ROC remains R, and here our ROC, okay, doesn't change. It's still our ROC remains what? R. It doesn't change. Okay, so here, what we're going to actually have is that we're going to see how this function can actually be proven. Okay, how this function actually can be proven. We know that the Laplace transform of x of what? T is, okay, the Laplace transform of x of t is what? Is what I'm going to write. So x is what? X of what? S, okay, it's like this. This equals to what? Integral infinity minus infinity. Okay, so x of what? T into minus what? St d what? dt. Okay, so now what we can do is that integrate both sides. So if I integrate both sides, then I'm going to have integral of what? S to what? Infinity. Because it's S domain, that's what I'm starting from what? S. Okay, integral of what? S to what? S domain. So I'm integrating this one, S of what? S. Here what? The S is equals to what? Here infinity minus what? Infinity. X of what? T. So here I'm going to integrate here S to what? S to infinity. Okay, E minus what? St. Okay, the what? The S. Okay, the S into, then I'll bring my what? My dt here. Okay, so this is what I'm going to actually have. So now if I have this one, then here I'm going to have here infinity, here is S. S of x of what? S. Okay, x of S is into what? The S is equals to what? If I integrate here with respect to the S, I'll have what? T, which will be what? Minus T. So I'll have integral here, infinity here, minus infinity. I'll have x of what? T over what? T. Okay, T over what? T. Okay, but my T here will be what? Negative. It will be negative. Okay, then I'm going to have here E minus what? St. Okay, and then here becomes what? The T. Okay, so now it is what? It is actually finished. It is actually finished, because if you look into this one, what you can see is that everything that you see here is this x of t and this e minus st is the what? Fourier transform that gives me what? X of s. And I know that x of s is the Fourier transform for x of what? T. Okay, for x of t. Okay, so now even if I repeat my x of t in the equation, because it's the same thing as what? X of s, because it's what? Fourier what? Transform, because it's Fourier transform. Okay, then in that case I can have what? X of what? T. That will give me the corresponding I mean, what I wanted to say here is that if I maintain my x, not really if I maintain, okay, what I am saying here is that this x of t e minus st is the Fourier transform that gives me what? X of s. And I know that x of s actually has a relation with what? X of t. Okay, so instead of writing x of s, I can write out x of t, because the Fourier transform of x of t will give me x of what? S. Okay, so here what I can write is that I can write here infinity and then here s. Okay, here x into what? S. Okay, into what? The s. Okay, is equals to what? X of what? T. X of t over what? Over t. Okay, over t. Okay, so basically that is what I can get over here. All right, that is what I can get over here. So it's, I mean, that simple. It's that simple that we should be able to always do it and then finish it up. Okay, so the ROC here doesn't what change. It remains the same. The RLC remains the same. Okay, so basically that is how you can actually do this one. Okay, I can have my negative come over here. Okay, so thank you so much. See you in the next lecture.